July 5th, 2025. A quiet night in Austria becomes the night the world meets three I/ATLAS. Amateur astronomer Michael Yerger spots a faint blue smear on his monitor, a ghostly streak cutting through the stars. It isn't in any catalog. Within minutes, observatories across Chile, South Africa, and Australia confirm it. The orbit is hyperbolic, proof it came from beyond the solar system. What shocks scientists most isn't its speed, but its weight, a mass so immense it redefines what a comet can be. True. The data pours in. Harvard astrophysicists start crunching numbers. They expect a typical comet, light, porous, the kind that sunlight can nudge off course. What they find instead forces them to rewrite the assumptions. 3 I/ATLAS carries a mass of 33 billion tons, a scale that rips through every known model of interstellar debris. Its core spans nearly 5 kilometers across, about the length of Manhattan. Normally, when a comet approaches the sun, solar heat boils away surface ice, producing gas jets that act like tiny thrusters. Even the smallest push should cause measurable drift. But Atlas refuses to move. Its path remains perfectly gravitational, locked in a curve so precise that computer models can't detect even a fraction of deviation. Avi Loeb, leading the Harvard team, describes it as an object that ignores physics. That phrase sticks. Astronomers begin calling it the cosmic mountain, a body so dense that light itself seems to slide off its surface without effect. Instruments tracking its path show no jitters, no spin variations, no trace of instability. It's not drifting like a snowball. It's advancing like a fortress in motion. By mid-August, the global network is in full swing. 227 observatories log more than 4,000 exact measurements between May and September 2025. Every reading repeats the same pattern, an unwavering trajectory, as if drawn by a ruler across the cosmos. The world's most advanced tracking systems expect turbulence, the kind caused by jets of gas pushing off the surface. But instead of chaotic variance, they find stillness. Astrometry shows zero measurable non-gravitational acceleration. The object should be twitching from all the expelled material, but it doesn't. Loeb's team takes the data and runs the simplest possible calculation. They compare thrust to acceleration. The jets are real, about 150 kilograms of gas every second shooting into space at 440 meters per second. Any small comet would wobble wildly under that force. But ATLAS, nothing. To produce this kind of stability, the mass must be astronomical. The math leads to one answer: billions of tons, minimum. Telescopes across continents confirm the same story. JWST, Hubble, and ground stations all show identical readings. The object is unflinching, a cold weight cutting through the solar wind like a bullet through fog. Observers start calling it an interstellar freight train, unstoppable, unshakable, moving with a precision that belongs more to machines than to natural debris. Then the chemistry begins to betray its own mystery. Spectroscopy from JWST and the Very Large Telescope in Chile adds a twist that no one expects. When cosmic material heats up near the sun, it usually releases iron and nickel together, twins born from the same stellar processes. But Atlas breaks that rule. Instruments detect pure nickel gas streaming off its surface, with no trace of iron. It's an impossible separation. In nature, the two elements are always fused. Something has filtered one from the other. And then there's the cyanide, sharp, sudden bursts in concentration that rise too fast for simple sublimation. Alongside it, carbon dioxide spikes at unnatural rates, inconsistent with known comet behavior. The chemical signature doesn't match rock, ice, or dust. It matches refined alloys and engineered surfaces. Loeb's group runs the numbers again. If the nickel is being selectively released, it could mean structured metal, possibly plates or coatings reacting under solar heat. It could mean construction, not coincidence. Debate ignites across every scientific forum. Is 3I/ATLAS an exotic comet from a distant system, its chemistry shaped by conditions we've never seen? Or is it something made, a manufactured relic designed to survive interstellar travel? Theories diverge fast. Some point to ancient planetary fragments, cores of long-dead worlds compacted into super-dense material. Others whisper of technological design, a megastructure traveling under camouflage, masquerading as ice and dust. What everyone agrees on is this: nothing in its makeup resembles anything seen before. Loeb writes in his field notes, "If this object is natural, it's rewriting the definition of nature itself." The scale of the mystery deepens as each new observation arrives. The mass, the composition, the perfect trajectory, they combine into a riddle that refuses to break. Scientists across agencies test for every possible explanation: carbon-rich ices, refractory silicates, hidden magnetism. Each test fails to account for the stability. Each dataset feeds the same truth: 3I/ATLAS is too massive to act like a comet, too precise to act like debris. Somewhere between physics and speculation, a new idea begins to take hold. What if mass itself is the clue? What if this isn't just a large visitor, but a designed object whose weight is intentional, a mechanism built to endure the violence of interstellar space? By late September, the tone in research circles shifts from disbelief to anticipation. Every new reading feels like a countdown. Telescopes realign, spectrometers recalibrate, and the world prepares for ATLAS's next move. Because for the first time, astronomers aren't just observing an interstellar object. They're witnessing something that feels alive not biologically, but in its control, its silence, its scale. And the question echoing through every lab and observatory is no longer, what is it made of? It's, who built something this massive, and why is it here now? The more scientists study 3I/ATLAS, the stranger it becomes. Every rule of cometary behavior bends in its presence, and every equation that once worked now trembles under its weight. The numbers are staggering, but what shocks researchers most is not how big Atlas is, it's how little it moves. Outgassing rates measured by JWST and Hubble are enormous. About 150 kilograms of gas per second, blasting into space at speeds of 440 meters per second. For any normal comet, that would be like strapping on rocket thrusters. Even minor gas releases have been known to push smaller comets thousands of kilometers off their projected course. But 3I/ATLAS remains utterly still, holding its trajectory with the steadiness of a planet. It's a paradox that astrophysicists have started calling the dead weight problem. The jets are there, visible, measurable, and energetic, yet the comet doesn't budge. For weeks, models have tried to reproduce the same result in simulation. Each one collapses under its own math. To stay this stable under that much thrust, ATLAS would have to be denser than solid iron. Its inertia dwarfs everything ever seen in an interstellar traveler. Harvard's Avi Loeb summarizes it in one line that now circulates across observatories. If it's moving, space itself is moving with it. That sentence captures the tone across the scientific world, awe mixed with disbelief. 3I/ATLAS has earned a new title, the heaviest interstellar object ever recorded. And the deeper the telescopes peer, the more it feels like mass is only part of the story. When orbital analysts map its course, they find another impossible pattern. Instead of plunging through the solar system at a random angle, as most interstellar objects do, ATLAS travels perfectly along the ecliptic, the same flat plane where the planets orbit the Sun. This geometry is so rare that probability models place it below 1 in a million. Yet Atlas follows it exactly, threading through the solar system like it knows the route. Its current path positions it for sequential encounters with Mars, Jupiter, and possibly Saturn, forming what some are calling a pre-planned trajectory. If that alignment were accidental, it would require cosmic luck on an absurd scale. The more likely explanation, some suggest, is that the path is deliberate, not in intent necessarily, but in precision. NASA's Mars Reconnaissance Orbiter and HiRISE camera are already locked onto coordinates for October 3, 2025, when Atlas will pass within just a few million kilometers of Mars. The moment offers a first in history, an interstellar object captured from another planet's orbit. Engineers are adjusting exposure plans for what could become the sharpest glimpse yet into the mystery. For now, though, the precision of its flight path remains its most haunting feature. Every kilometer of motion appears calculated. Every drift fits the plane of the planets like a train running on invisible rails. Then comes another puzzle. Observers tracking light from ATLAS begin to notice something that shouldn't exist: a faint, persistent glow that refuses to match the reflection patterns expected from sunlight. The luminosity holds steady even when the object's angle changes. Reflection should dim, but it doesn't. The implication is staggering. If that glow isn't reflected sunlight, it could mean ATLAS is producing its own energy. The question becomes, how? Engineers studying spectrographic data note rhythmic fluctuations in brightness, not random flares, but measured pulses, almost mechanical in rhythm. Some speculate this could point to internal heating, possibly nuclear decay, or a fusion process sustained beneath its crust. Others go further, theorizing it might possess vent arrays or power conduits distributing heat evenly across its surface, preventing uneven jetting that could disturb its perfect motion. If you're fascinated by what scientists are uncovering about 3I/ATLAS, make sure to subscribe and leave a like. There's much more coming as the mystery unfolds. The reflective symmetry adds weight to the speculation. Certain panels catch light at predictable angles, repeating every rotation cycle. These reflections appear too regular, too clean, to come from natural fractures. To many, the conclusion is difficult to ignore. Whatever is inside Atlas isn't chaos, it's structure. A vast internal system maintaining control, distributing power, and holding course with precision. If this is true, it would make Atlas not just the heaviest interstellar traveler, but a functioning machine. An engineered object capable of interstellar endurance, cloaked in dust and gas to blend into the cosmic background. The discovery fractures the scientific community in two. At NASA and JPL, analysts double down on the natural explanation. Their official position remains cautious. Atlas, they argue, is a dense CO2-rich comet with a thick, slow-spinning nucleus that stabilizes its motion. They point to the observed gas composition, heavy in carbon dioxide, low in water, as consistent with formation in a cold stellar nursery. But across the Atlantic, the tone is different. Harvard's Loeb team insists the evidence points toward artificial origin. They argue that the near-perfect ecliptic alignment, the absence of measurable acceleration, and the metallic spectral lines together form a picture too coherent to dismiss. To them, 3I/ATLAS isn't an accident of nature. It's a construct, a probe disguised as stone and ice, using its mass as camouflage. The debate turns philosophical. If a body this massive, this stable, and this geometrically aligned is natural, then the definition of natural itself collapses. But if it isn't, if it was made, then humanity may be standing on the edge of its first confirmed encounter with alien engineering. The internet takes over where academia hesitates. Hashtag Atlas Titan trends worldwide. Memes, simulations, and speculative artwork flood timelines. Some celebrate it as proof that intelligent life exists beyond Earth. Others treat it as an omen, a silent visitor reminding us of how small we are. Governments stay quiet. Research institutions issue brief statements. Behind the silence, one truth lingers. This discovery has broken the boundaries of science fiction. 3I/ATLAS has become a symbol, not of fear, but of the unknown. Amid the controversy, a team at Zhenjiang Laboratory in Shanghai pushes the story even further. Their simulations test what would happen if interstellar giants like ATLAS regularly cross young planetary systems. The results are transformative. When an object this massive, a 5-kilometer-wide body weighing 33 billion tons, passes through a protoplanetary disk, it acts like a cosmic fertilizer, spreading heavy elements, rare minerals, and organic compounds. Each encounter accelerates the birth of new worlds by tens of thousands of years, seeding the ingredients of life where dust alone could not. According to Zhang's models, such interstellar titans could be the builders of planets, the catalysts of creation itself. The simulations even suggest that our own solar system may owe part of its composition to a similar visitor billions of years ago, a predecessor to 3I/ATLAS that shaped the early Earth. For centuries, comets were seen as harbingers of doom. But maybe, just this once, one has come to deliver knowledge instead.